All right, we're going to be doing double angle formulas now. So double angle formulas happen quite a bit, and you're going to see them in calculus. They're extremely useful when you're doing something called integration. So I'm going to show you where they come from. Sine of 2x. It is called a double angle formula because you double the angle. But the way that we think about it is not double angle. We think about it like sine of x plus x. And then this is our alpha and our beta for the angle addition. And this is just a shortcut. We could do this every time, but it's useful to memorize what sine of 2x is so you can quickly substitute instead of doing this every time. But I'll show you where it comes from. And remember, sine angle addition is sine, cosine, cosine, sine. So this would be sine of x, cosine of x, plus sine of x, sine, cosine, cosine, sine. So we should be really writing it like this. And I was thinking in my head already that cosine and sine, because they're being multiplied, they can be flipped around. It's called commutative. You can flip the order in which you multiply. If you flip them around, what you get is sine of 2x is the same as 2 of the sine x cosine x's. Okay. So actually, when you get into calculus and you're doing integrals, you would end up with something similar to the right side, which is impossible to integrate the way it is, or it's hard. The other side is much easier to integrate. So keeping this in mind will help you later on. All right, now that's sine of x. Let's talk about cosine of 2x. Cosine also has a double angle formula. First, we're going to think of it again as cosine of x plus x, and then we're going to do the angle addition formula. So that one is cosine, cosine, sine, sine, sine. If this is alpha and beta, this would be cosine of x minus the sine of x, sine of x. Okay, and simplifying this, we get cosine squared x minus sine squared x. All right. So that is one of the identities. There are actually 3 of them. So I'm going to show you where the other 2 come in. You can actually take this and use a Pythagorean identity to rewrite it. What is cosine squared x? Well, it's actually the same as 1 minus sine squared x minus sine squared x. You'll notice here there's no distribution. I don't need those parentheses. So I could rewrite it as 1 minus, and there are 2 sine squared x's. And so this is the second of the double angle formulas for cosine. We're going to do the same thing for the third one. If we replace sine squared in, we could rewrite it as cosine squared x minus the quantity 1 minus cosine squared x. So in this case, we're changing everything to cosine instead of sine. Now, you have to remember to distribute the negative here. So you will have 2 positive cosine squareds, and you're going to subtract 1. So lucky cosine gets not 1, not 2, but he gets 3 different formulas. So one thing I just want you to be careful about here, this is often confused with the Pythagorean identity. Remember that Pythagorean identity is the sum of the squared sine and cosine. Okay? In this case with cosine of 2x, it's the difference, and those guys are fundamentally different. One is the difference, one is being summed, and no matter how many negatives you put on the Pythagorean identities, if you're doing legal operations, you're never going to get the other guy. You're never going to get this double angle thing. So those are 2 very similar looking identities, but they are not the same. Also, we should probably talk about tangent of a double angle. Now that we're going to use it in the same way, we're going to think of this as x plus x. And if you remember back, that's going to be tan x plus tan x all over 1 minus, and then we'll have 2 tan x's down here. So that simplifies actually to be 2 tangent of x all over 1 minus tan squared of x. So as you can see, if you know the trick and you know the angle addition formulas, it's not easy, it's not hard to derive them and find them every time, but it might save you some time if you just have them memorized, and then later on it'll be easier to recognize. So I want to show you one last example before we end. I want to show where this might actually come up in an identity. So for example, we have sine of 4x on one side, and we have to show that this is 4 sine x cosine x 2 cosine squared x minus 1. It's a mouthful. Now on the right side, it is more complicated looking, but we're going to keep using the same trick that we've been talking about. And that is, look at this argument, this 4x, and break it up in a different way. Instead of writing it 4x, what I'm going to think of this as is sine of a double angle, and that angle is going to be 2x. So this is the form of sine of 2 times an angle. Now you remember, sine of 2 times an angle is the same as 2 sine of that angle cosine of that angle. So we're going to rewrite this as 2 sine of the angle. And when I say angle, I mean 2x right now. Cosine of 2x. Okay? Now what made me think about this? What made me think about this was that these look very similar to double angle formulas, right? And so I want to keep a double angle formula in there. And so I would write sine of 2 times a double angle. Now this could be rewritten now as, well, sine of 2x would be 2 times sine of x cosine of x. That is just the straight up sine of a double angle. This right here is 2 cosine squared x minus 1, which is just the third cosine double angle formula. And then the last thing we need is this 4. So we just multiply 2 times 2. Okay, and there we have it. We've gone from the left side and shown our steps until we've reached on the right side.